When electrons flow through loads or resistors, there is dissipation of energy. The rate of dissipation of this energy is what we call power. When we say an electric kettle is rated at 50 watts, it means the rate at which it is dissipating energy is 50 joules per second. Likewise, a bulb rated 3 watts means it's dissipating energy at a rate of 3 joules per second. However, in electricity, sometimes the electrical power is expressed in terms of kilowatt hours. Think of the kilowatt hour as a unit that is used to quantify the amount of electricity. Let me use an illustration. Let's take a case in point. I have this cup right here. Inside it there is some sugar, right? I have a spoon right here. Now let's imagine that I am having a very big bag of sugar. This bag is filled with sugar, but I want to sell this sugar. I want to distribute it. Now, I have two options. I can either use this cup to distribute this sugar, or I can use this spoon. If I am to get this spoon and use this spoon to distribute sugar that is in a sack, I'm really going to take a lot of time, right? But it is more convenient if I use this cup. Now, I can use this spoon, yes, and I can say that each sugar that I'm going to give out, each spoon of sugar costs 100 shillings. And so if somebody came with a very big polythene bag and they want, let's say, they want the polythene bag to be filled with sugar, it means if I'm selling each spoon at 100 shillings, I'll keep scooping from the big sack to be able to sell, to give to this person, but it will take me a lot of time because this spoon is too small. So definitely the convenient choice would be for me to use this cup, because with this cup I will be able to give out too much sugar within a very short time. So what does that mean? It means that instead of using this spoon, I'll use this cup as my unit. So I'll say every cup of sugar that I give out will cost me, I'll expect a payment of, let's say, like 1,000 shillings. So now this cup of sugar becomes my unit, or the standard upon which I'm going to use to sell sugar. So this same analogy is the same when it comes to electricity and billing of electricity. We know that electricity is when it's flowing, energy is dissipated, and the rate of this dissipation of energy is what we are calling the watt. So now, just like this illustration I've used, when the utility companies are billing electricity, they can bill it in terms of watts, and billing it in terms of watts could be equivalent to billing electricity using this spoon. But you see, we use so many watts of electricity every other day, and it would become tedious for the electricity company. We already determined that electricity flows in terms of watts, and 1 watt of electricity is 1 joule per second. So just imagine that that watt or that joule per second is like this spoon. And now I am giving out electricity to the people. If I give out electricity to the people while I am using the standard that I'm going to measure the electricity, or I'm going to bill electricity in terms of watt, 1 watt, it's going to become tedious. So what do? I say that I'm going to get this 1 watt of electricity and count 1,000 watts. So I'm going to group the electricity in terms of 1,000 watts, 1,000 watts, 1,000 watts. So when I have 1,000 watts collected, that is equivalent to this cup. So it means I will be selling electricity in terms of 1,000 watts. So it means I create a standard and say that 1,000 watts of electricity is equivalent to 1 unit of electricity. Let's first look through this here. We know that power is going to be equal to work done over time taken, and 1 watt, which is the SI unit for power, is 1 joule per second, which is that. However, when we are billing electricity, we are going to collect the watts into 1,000. So that's why the kilo comes in. Kilo means times 10 to the power 3. So 1 kilowatt is 1,000 joules per second. Then 1 kilowatt, if we multiply that by 1 hour, it means that it's going to become 1 kilowatt hour. If you to multiply times the hour, it's going to become 1,000 joules per second. Multiply that by the hours. In 1 hour there is 3,600 seconds, so it's going to be 3,600 seconds right there. When we cancel the second there and the second there, we remain with 3,600 times that, giving us 3.6 times 10 to the power 6 joules. So it means in 1 kilowatt hour, there are 3.6 times 10 to the power 6 joules of energy. So now this 1 kilowatt hour instead is the standard that is used by electricity utility companies in the billing of electricity. Liken it to this scenario, that instead of using this spoon to measure the sugar that I'm giving out as I'm selling, instead I'll use this cup. It is easier for me to scoop this cup, and I'll simply say that, okay, every cup that I am selling, I'm selling it at 1,000 shillings. So this cup is like the kilowatt hour, and this spoon is like the watt, the joule. So instead we're using this. So meaning that when we are billing electricity, we are simply going to use the kilowatt hour. So by definition, the kilowatt hour is the amount of energy that is supplied at a rate of 1,000 watts for 1 hour. And the number of joules of energy that are in 1 kilowatt hour are 3.6 times 10 to the power 6 joules, and this is how we're able to get those joules of energy. So in today's session, I get to explain how we calculate for the kilowatt hour in the billing of electricity coming up. An example, how much will it cost to run 2,000 watts electric fire running for 45 minutes if electricity costs 425 shillings per unit? Now we are aware that this unit they are talking about is actually 1 kilowatt hour. So it means that they're telling us that 1 kilowatt hour of electricity costs 425 shillings. So the question here is that we're supposed to compute how many kilowatt hours are in this electricity that is being consumed. Then when we are able to compute the kilowatt hours, then we are able to compare and see how much we are going to pay. So this one is running a 2,000 watt electric fire, and it's running for 45 minutes. So since it is 2,000 watts, it is running for 45 minutes. We're supposed to first convert this into kilowatt hours. When we convert it to kilowatt hours, then we are able to determine the cost. So it is running 2,000 watts. Those are 2,000 watts. So it means that 2,000 watts, to convert those to kilowatts, it means it's going to be 2,000 divided by, of course, 1,000 to make them 2 kilowatts. Now converted those kilowatts into hours. It means you're supposed to multiply this by the hours this thing was running. Now they're telling us that this 2,000 electric fire is running for 45 minutes. Now converting 45 minutes into hours will mean it is 45 minutes divided by that by 60 minutes. So it's going to become 2 kilowatts times the hours, which is 45 minutes divided by 60 minutes to convert this to hours. So it's going to become, by 15 is thrice, by 15 is 4 times. So it's times 3 over 4. This gives us by 2. So this becomes 1.5 kilowatt hours. So after computing it and converting it to kilowatt hours, now we can go ahead and know that 425 shillings is the cost of the unit, and the unit is a kilowatt hour. So we know that 1 kilowatt hour costs 425 shillings. So what about 1.5? So meaning 1.5 kilowatt hours will cost how many shillings? Put the unknown. When you cross multiply x times that, x is going to be this times that, which is 1.5 times 425, and therefore that will give us 637.5 shillings. In our other example here, we are being told that Umeme charges 425 shillings per kilowatt hour. Now Umeme is an electricity utility company in Uganda. Umeme charges 425 shillings per kilowatt hour of electrical energy consumed. What is the total cost of operating 4 light bulbs rated at 100 watts each for 5 hours? So again, we need to first compute the kilowatt hours that are being consumed. Now according to this question, they're telling us that there are 4 light bulbs. So there are 4 bulbs Now each of these bulbs is rated at 100 watts. So it means that the total wattage that is being consumed by these bulbs is going to be 4 bulbs multiply that by 100. So together all these bulbs are consuming 400 watts. So now, but they are consuming them in 5 hours. So let's first convert these watts to kilowatts. Converting these to kilowatts, we divide that by 1000 and we are going to end up with 0.4 kilowatts. Now, so converting those kilowatts to kilowatt hours, it means you're supposed to multiply this by the hours it is running. So of course, multiplying that by the hours, it means this thing is running for 5 hours. So it means it's going to become 0.4. Multiply that by the 5 hours. And so 0.4 times 5 hours gives us 2.2 kilowatt hours. So it means that these 4 bulbs running at 100 watts each for 5 hours, they consume 2 kilowatt hours. So if they're telling us that every kilowatt hour is that much, we're able to get how much it's going to be. And in this case, we know that 1 kilowatt hour is going to cost 425 shillings. Therefore, 2 kilowatt hours is going to cost this times that, twice the other. So it means that is X giving us 2 times that, 425, and of course. So now how much energy is present in just 1 kilowatt hour of electricity? So let's try and find the number of joules in 1 kilowatt hour of electricity. First of all, we know that work done, or let's call it energy. Energy is always measured in joules. And the power is the rate of change of this energy, or the rate of change of work. So meaning that power is going to be equal to the rate of change of energy, which is going to be energy over time. Power being energy over time means that it is energy is always in joules and time is always in seconds. So it means that power, or 1 watt, because joule per second power is measured in watts. So it means that 1 watt is going to be equal to 1 joule per second. But now here we want to find out how many joules are in 1 kilowatt hour. I hope we all know that kilo means times 10 to the power 3. So it means that if 1 watt is equivalent to 1 joule per second, what about 1 kilowatt? 1 kilowatt will mean that is times 10 to the power 3 here. So it means it's going to be 1000 joules per second. But then here we're interested in finding 1 kilowatt hour. So it means that 1 kilowatt hour will mean it is going to be 1 kilowatt, which is, we've already gotten as 1000 joules per second, times the number of times the hours, which are equivalent to 3600 seconds. So it's going to be 1000 joules per second. That is what we have in the kilowatt. Then these hours, we're supposed to convert them to seconds, because we are multiplying joules per second. Multiply that by second. So it means 1000 joules per second. Multiply that by 3600 seconds. So 3600 seconds is what is present in 1 hour. So that as you're multiplying joules per second by a second, you remain with joules. So it means that the answer we have here is 3.6 times 10 to the power 6 joules. And these are precisely the number of joules that are present in 1 kilowatt hour of energy. Let's look at an example here. Per unit of electric energy is 300. What is the cost of operating 6 bulbs rated at 75 watts, 220 volts for 8 hours? We want to find the cost per unit of electric energy. I mean, want the cost of operating 6 bulbs. So we have 6 bulbs, and each of these bulbs is rated at 75 watts. So it is 75 watts times the 6 bulbs. So how much energy are they consuming? So there are 6 bulbs, each at 75 watts. 75 times 6, that is going to give us 450 watts altogether for these 6 bulbs. So converting this 450 watts into kilowatts, because we're supposed to convert this in terms of kilowatts. So it means that divide this by 1000. So it comes to 0, that is 1, 2, 3, 0.45 kilowatts. So the bulbs are consuming 0.45 kilowatts in just 1 hour. So we're supposed to find how many kilowatt hours are being consumed by these 6 bulbs. So the amount of kilowatt hours consumed by those 6 bulbs is going to become, since they are 6 bulbs and they are operating for 8 hours. So it's going to be 0.45 kilowatts, multiply that by the 8 hours. And 0.45 kilowatts, multiply that by 8 hours, you'll get 3.6 kilowatt hours. So you get the kilowatt hours that are operating by those 6 bulbs. But now the question is telling us that the cost per unit of electricity, and the unit of electricity we are talking about here is the kilowatt hour. So the cost per unit of electricity is 300. So what is the cost of operating these 6 bulbs? So we know that 1 kilowatt hour is equivalent to 300, probably shillings or dollars or whatever. This is the cost of 1 kilowatt hour. How about this 3.6? So it means that 3.6 kilowatt hours are going to be equivalent to, you put there x or an unknown. When you cross multiply, your value of x will be 3.6 kilowatt hours times the unit, the cost, which is 300, and you'll get your answer as 1080. That's the cost per kilowatt hour. Let's do one more number. Umeme is a utility company. It's a utility company in Uganda. Umeme charges 300 per kilowatt hour. What is the total cost of operating 4 light bulbs at 100 watts for 5 hours? So we have 4 bulbs, and each of these bulbs is rated at 100 watts. So it means that total rating for these bulbs is going to be 4 bulbs times 100 watts. So it's going to be 400 watts. But now these watts are this wattage, let's say they are running for 5 hours. So we multiply this by the 5 hours. So it's going to be 400 watts. Multiply that by the 5 hours and you end up with 20. You end up with 2000 watts. But now this is 300 per kilowatt hour. So it means that you're supposed to convert this to kilowatt hours, because this is how much is consumed in 5 hours by these 4 bulbs. Convert it to kilowatt hours. So converting this to these watts to kilowatts, you simply divide by 1000. When you divide by 1000, 2000, divide by 1000, you end up with 2 kilowatts. So it means that these bulbs are going to consume 2 kilowatts in 5 hours. And now we are supposed to find the total cost of operating those 4 bulbs for 5 hours. So since we know that 1 kilowatt costs 300, 1 kilowatt hour costs 300 shillings, whatever. So it means that 2 kilowatts will cost twice that. Let's say it will be x. When we cross multiply, x times 1 is x, is going to be equal to 2 times 3 is 600. And that will be the cost of operating those bulbs. An electric kettle is rated 2 kilowatts, 240 volts, and when it's filled with cold water, it takes 5 minutes to boil. calculate the resistance of the element when the kettle is in use. So for us to get the resistance of the element when the kettle is in use, remember we are looking at electric energy and power. So they've given us the voltage, they've given us the power, and they're asking us to find the resistance of the kettle element when it is in use. Now there are a few things that in our previous videos we derived the three equations of energy and power. The work done in moving a coulomb of charge from one point to another within a conductor is what we are calling the potential difference between those 2 points. If we are having 1 coulomb of charge flowing here, 1 coulomb, it's 1 coulomb of charge that is flowing, and the potential difference across the ends here is 1 volt. It means that the work done in transferring this coulomb from this point to that is going to be 1 joule, because the work done is going to be equal to the voltage, multiply that by the charge. So meaning that the work done to move 1 coulomb of charge between 2 points with a PD of V is going to be 1 times V, which is V joules. Likewise, the work done in moving Q coulombs of charge between 2 points at a potential difference of V is VQ joules. So, in essence, work done is going to be V times Q. The potential difference across those ends, multiply that by the number of coulombs that are being transferred. That's the work done. Also, in our previous videos, we said that the current is the rate of flow of charge. So if you're having charge, that is it, current is the rate of flow of charge. That makes Q be equal to current times the time, IT. So meaning that if we are to dance around with those two, we say that work done, deriving from this equation, we know that work done in transferring 1 coulomb of charge from one point to another is going to be given by V times Q. But we know that Q is going to be equal to current times T, so we substitute for the value of Q here. So it means it's going to become V times I times T. That is work done, VIT. And so now this becomes our formula for the energy. Energy is going to be V times I times T. That is one formula for energy. We can also, if we are to substitute for the value of V, remember that V is going to be IR. So if you are to put IR in the place of I, in the place of V, substitute, it means that our value energy is going to be equal to, electric energy is going to be I times R in the place of V times IT times I times T. So that is going to become I squared R times T. That's another expression you can use when you're calculating for the value of energy. We know that I is equal to V over T. So likewise, like before we substituted for the value of V, now we can substitute for I in this expression and we put V over T. So it means that our energy here is going to become V times I is V over T times T. So it means it's going to become V squared, this is V over R, sorry. So it's V over R. So that's V squared over R times T. And that's our formula for energy. So in our calculations, you can either calculate for energy using either this equation, this expression, or this expression, or that expression. Either way. So let's get to some of the expressions we shall be using when we are calculating for power. First of all, what is power? Power is the rate of dissipation of energy. So it means that power will be equal to energy over time. That is power. So if power is that, so it means that for our formulas of energy, for example, if you want to express the expression for power, we know that energy is V of V I T. That is the expression for energy. So it means that our expression for power will be over T. Power will be equal to V I T, divide that by time. So electric power will be VI. That is one expression. We can have another expression for energy from our second equation here. We know from there that energy is equal to I squared times the resistance times the time. So it means that our power is going to be powerful from this expression. Power is going to be equal to I squared R T, divide that by time. So this T dies with that, you remain with power as I squared R. That's our second expression. And our third expression, we have energy is going to be V squared, is going to be equal to, in our third expression, if energy E is going to be equal to V squared over R times T. So it means that power, our value for power is going to be, power will be equal to V squared over R T, divide all that by T. This T will die, so you have power as V squared over R. So those are our expressions for energy, and these are for energy, and these are our expressions for power. Let's try and review them. We know that power is going to be current times voltage. That is electric power. If we are to substitute the value of I, we know that I is equal to V over R. If you are to put here V over R, it will mean that power will be equal to V squared over R. Or if we are to substitute for the value of V and we put V is equal to IR, so we substitute this part with I times R, which is current times resistance, then our formula for current can also be P is equal to I squared times R. We derived these three formula in our previous videos. These are formulas for power. So we're supposed to choose from one of these three to solve this problem. Now from here they are asking us to find the resistance of the element when the kettle is in use. So it means we shall concern ourselves with formula that have got the element of resistance in them, and this is this one or that one. So from these two, which one shall we pick? According to our question, we have power, 2 kilowatts, so we have power. We have voltage, so we have voltage here, but we do not have any voltage here. So meaning we shall take this because it has power voltage and they're asking us to find the resistance. So we shall use the second one. So here, power is going to be equal to V squared over R. Our power is 2 kilowatts. 2 kilowatts is going to be equal to V squared, which is going to be 240 volts. Divide that by R. When we make R the subject of the formula, it's going to be 240. Divide that by 2 kilowatts, which is equivalent to 2000 watts. This is 40 volts. So 240, divide that by, remember this is squared, right? Yeah, this is squared. 240 squared. 240 squared divided by 2000 will give us 28.8 ohms. And that will be, or that is, the resistance. That is the resistance. So let's look at Roman 2 of the question. Roman 1, they're asking us to find the resistance of the element when the kettle is in use. Question. So they're asking us to find the average weekly cost of using the kettle, assuming that it is used 6 times each day. So it means that we are supposed to find how many kilowatt hours are spent in a week, because they are asking us to find the average weekly cost. So we find the kilowatt hours that are used every week. After getting the kilowatt hours that are used every week, then we can find the cost of those kilowatt hours that are used every week. So we begin each day. And remember, according to our question here, they're telling us that it takes 5 minutes to boil the water, right? That when filled with cold water, it takes 5 minutes to boil the water. So 5 minutes is the time taken to boil the water. And they're telling us here that they use it 6 times a day, and when they use it those 6 times, they put cold water which is boiled. So we find, so it is going to be, so daily use, for us to use it daily, they are going to use it 6 times, and each 6 times it's going to take 5 minutes for that water to boil. So 6 times 5 is going to be giving us 30 minutes. So each day it's going to spend 30 minutes, and that is going to be 0.5 hours. So that is 0.5 hours. Now, if daily it's going to be 0.5 hours, what about weekly? How long is it going to be used weekly? So weekly, the weekly usage will be these 0.5 hours every day, multiplied by that by the 7 days of the week, and it will give us 3.5 hours in a week. So we know that every week this kettle is used for 3.5 hours every week. But what is the rating of this? Now we get the kilowatt hours. What's the rating of this kettle? It is 2 kilowatts. That is its rating, 2 kilowatts. So if its rating is 2 kilowatts, so meaning that the kilowatt hours, the weekly kilowatt hours will be, it is 2 kilowatts, multiply that by the hours it spends running in a week, which is 3.5 hours. That's going to be 3.5 hours. And that's going to give us 7 kilowatt hours. So after getting the 7 kilowatt hours, now we find the costs per week. So the weekly cost will be 7 kilowatt hours. Multiply that by the cost per kilowatt hour, which is 300, and it will give us 2,100. Fire is operated from a 240 volts AC main supply, and it's rated at 1.5 kilowatts. When operating at a rated power, calculate the current used by the fire. We are going to do these three. Let's start with the first one. They're asking us to calculate the current used by the fire. From our equations of power, P is going to be I times V. This is Roman 1. Current times voltage. What is our current? They are asking us to look for the current. What is power? It is rated at, do we have the power? Current used by the fire is what we want. The electric fire operated from that AC mains is rated at 1.5 kilowatts. So meaning that our power is 1.5 kilowatts. So it's going to be 1.5 kilowatts is going to give us current, which you are looking for. Multiply that by the voltage, and here the voltage is 240 times 240. So meaning that our current is going to be equal to 1.5 kilowatts, which is going to be, if you multiply this, convert this to watts, it means you're going to multiply this by 1,000. It's going to become 1,500 watts. Divide that by 240 volts, and it means that our current is simply going to be 6.25 amperes. That's the current. We go to Roman 2. The energy given out by the fire in 10 hours. Now we know that power is the rate at which work is done. And we know that when work is done, that is energy, meaning that power is going to be the energy over time. So it means that to get this energy, the energy given out by the fire in 10 hours, it means that energy is going to be equal to the power times time. Power times time. This is Roman 2. What is our power? Our power is 1.5 kilowatts, so it's 1,500 watts. Multiply that by the time. The time is 10 hours. So it is 10 hours but we are supposed to convert those hours into seconds. So it's 10 hours times the 3600 seconds that are contained per hour. So it's 10 times 3600. So it's 1500 times 10 times 3600 is going to give us 5.4 times 10 to the power 7 joules. And this is our energy. So let's look at Roman 3. They're asking us to find the cost of running the fire in 10 hours if the cost per kilowatt hour is 300 Uganda shillings. So now, how many kilowatt hours are generated within 10 hours? So we know that this electric fire is rated at 1.5 kilowatts. So if it is rated at 1.5 kilowatts, this is Roman 3, the rating is 1.5 kilowatts. So meaning, therefore, the kilowatt hours in 10 hours is going to be the rating, which is 1.5 kilowatts times the 10 hours. So this is going to give us 15 kilowatt hours. But then the cost of 1 kilowatt hour is 300 shillings. So if the cost of 1 kilowatt hour is going to cost 300 Uganda shillings, so it means that 15 kilowatt hours will be 15 times that. It will be 15 times 300, and you end up with the answer as 4,500 Uganda shillings. And that will be the cost for running that fire. So you can try out these numbers. Remember, the concept is very simple. You have to first compute how many kilowatt hours are being produced. Then you relate those kilowatt hours to the cost of each unit to be able to get how much. So that's the end of that question. You can let me know of the answer you get in the description below. That right there is another question. You can still do it using the same concept. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.